Hi, I put together a short video for the notes on section 3.1 functions. And so let me get started on that. So if you look at the ideas from sections 3.1, it's talking about defining what a function means. And it's any situation where one quantity depends on the value of another. We can think about that relationship as a function. And so there can be lots of different examples. The price of an object is a function of the demand. If you tell me if it's high demand, then the price is probably going to go up. If it's nobody wants to buy it, then the price is going to have to go down. There's a relationship there. Or you can say the population of Ohio, as it changes over time, is a function. You tell me what year you're talking about, and I can tell you the population of Ohio. There's a relationship there. The time it takes to drive to New York is a function of your speed, your average speed. If you tell me what your average speed is, I can figure out there's an output of how long it's going to take you to drive from Marion to New York. How much a bridge can support is a function of its length. The grade you receive at the end of this course is a function of how much you study. Those are all functions. Those are all relationships between one value and another, but they're different in some important ways. The orange ones here, the price of an object depends on the demand, and the grade you receive depends on how much you study. Those are more general relationships. They're not precise functions. If you increase the demand in an object, you can probably increase the price. If you study more, you probably get a better grade. There's a general relationship there, but that's not a precise function as we talk about mathematically. But the other three are in certain ways. So the population of Ohio as it changes over time, you can look at a chart, and if you tell me a year, say 1950, I can look at that chart and figure out what the population was. It was about 7.5 million people in 1950. Or you ask me in the year 1900, I look at 1900 and the population was about 4 million. There's a relationship that if you tell me the year, I can tell you a population. There's no algebraic expression for that. It's not 3x squared minus 7 or anything, but there is a function and there's a rule you can follow to find the answer. It might just be in a chart. Another type of function might be over here on the right, the time it takes to drive to New York as a function of your average speed. The horizontal axis, you can graph it. The horizontal axis over here is going to be the speed. You tell me how fast you're going. The vertical axis is how long it's going to take you to drive. If you are going 100 miles an hour, it's going to take you 5.4 hours because it's 540 miles from Marion to New York. If you go half as fast, 50 miles per hour, it's going to take you twice as long, 10.8. And that. And in this case, you could chart it, but you also have a formula. There's a formula, an algebraic expression for the time in hours. If you tell me X miles per hour, the time for that speed is 540 divided by X. There's a formula for it. So some functions have expressions, algebraic expressions. Some functions have just a chart. Some functions like how much load a beam can carry depends on, you have to tell me what kind of beam it was and how long it was. And if it's 106 inches long, then that can hold 6,584. There's no formula there, but there's a rule that you can follow and get an answer. So those are all different sorts of functions, different ways to represent functions. Typically, we're going to expect them to have a graph, or most of the time a function that we can at least model to determine the relationship. So what's a formal definition for function? The formal definition is something like a function is a rule that assigns to each element that you plug in exactly one element, the output, and it's called f of x. So there's an input and an output. And for every input, there has to be exactly one possible output. So if you tell me how the radius of a circle, I can find the area. There's a formula for that. If you tell me how long after a ball has been dropped, there's a rule to tell me how high the ball is. If you tell me the volume of a cube, there's a rule to find the length of the side. I can find functions for all those things. So let me give you some examples, some terminology. So an independent variable is the variable that is input into the rule, into the function. The dependent variable is the resulting value. It depends on the input, right? So if you plug in a value that's the independent, it can be whatever you want. And what comes out depends on what you plugged in. That's the dependent variable. And you might have heard the domain of a function is all possible inputs. Usually it's the x values, but not always. The range is all possible outputs. Again, usually that's the y values or the vertical axis on a graph, but not always. And in examples could be like the example of the radius and a circle. If I want to find the area of a circle, you tell me what the radius is, and I know a formula that area is pi r squared. What's the domain of that radius or of that function? As an algebraic expression, I can plug in any number I want from negative infinity to infinity. I can plug in positive or negative and get an actual answer. But in a practical sense, the radius of the circle has to be positive. So there are kind of a formal domain, and then there's a practical domain for a lot of problems. That probably only works for radius larger than 0. An example for the time that a ball, the height of a ball after it's been dropped t seconds later, after t seconds, might be this quadratic formula, negative 16t squared plus 10t plus 8. That's a formula we'll talk about, but the domain for that is all real numbers. I can plug in any value for t and I can get an expression or get a value. But in practical sense, if you're actually plotting a graph, the domain is, that formula is only valid from the moment you drop the ball, so this should be greater than or equal to 0, until the object hits the ground, and then that formula no longer applies. So again, I want us to think about the formal domain that you might see where it could be all real numbers, but then in any realistic problem, there's often a practical domain where it only really applies in this certain instance. So now I want to talk through some of the example problems from the homework. So again, for the homework, I'm going to ask you to do the problems that are highlighted in purple on this handout. So for this set, it would be 9, 10, 12, and 13. I'm going to talk about how to do 11 as an example, and we'll do more in class tomorrow. But this says determine whether the relation represents a y as a function of x. So as a function of x means that's the independent variable. And if y is a function of x, y is the dependent variable. Y would depend on what x is. And it's going to be a function if, what it says here in purple, there's exactly one possible value of y, the output, for every possible x, every possible input. If that's the case, then it determines a function. So for number 10, x equals y squared is not a function. There's two ways you can show that. One is if you can find two different values of x to plug in, or of y, that correspond to x, two possible outputs, then that's not a function, because you tell me the value x, there are two possible answers. Well, y could be 2 or y could be negative 2. So it's not a function in that sense. It doesn't determine what the output is going to be. Another way to check if something's a function is to try and solve for y in terms of x. So you take that expression, x equals y squared, and try and solve for y using whatever algebra is necessary. And in this case, we get plus or minus the square root of x. And if you see something like a plus or minus, that gives you two possible outputs for the y, two possible values for the y. And so that violates the rule of a function as well. So in this case, it's not a function. Another way you might have seen this is the vertical line test. So think about how, if you try and draw a graph of a curve and it crosses a vertical line twice, why would that violate the idea of a function? Think about that. Here's number 12. Again, 2x plus y squared equals 6. That's the expression. That's a relationship between x and y. If you try and solve for y, you get plus or minus the square root of something. So in that case, as soon as you see that plus or minus, you know it's not a function as written, because y could have, in a lot of cases, could have two values, plus the positive or negative. However, if you change the exponent to a cube, think about why the cube root is fine. You don't get plus or minus the cube root of 6 minus 2x. You just get the positive cube root. So for real numbers, that does define a function. So then if we skip down a little bit to some other examples, in this, you're supposed to evaluate the function at certain values, that just means plug in the expression, -3 or -a or a plus h. Plug that expression in to the function. But I wanted to point out number 32 and 33. They have this weird expression to simplify g of x minus g of a all over x minus a, this expression. So what you do is you plug in the expression for g of x and you plug in the expression for g of a, and then the rest is this to simplify that expression. And the goal of this is to be able to cancel out the x minus a in the numerator and denominator. So if you follow through multiplying this out, doing some factoring, eventually you can cancel out the x minus a's. And that's the goal of this, this type of expression. You might not have seen an expression like that before. You might be wondering why that's there, because it's in every pre-calculus textbook. And here I'm going to try and explain why that happens. So why do we care about this horrible expression? For some function, g of x, and some point a, some value a, why do we care about g of x minus g of a, the whole thing divided by x minus a? Well, here's the idea. Consider your function g of x. In this case, it's x squared plus 2x. So I graph that, and that's a parabola, like we've got there. And what they're asking us to do is look at the point x and some other point a. And in general, a is going to be close by, and I'll explain why in a little bit. But this expression, what's the slope between the point on that curve at x and a? Well, the slope, it's a curve, so the slope is changing a tiny bit as you go. But if x and a are close by, then that line is pretty close to the curve. Between those two blue points, the curve doesn't change slope very much. So we can use that as an approximation for the slope of the curve. And so that the rise is g of x minus g of a, which is the difference between the y values, and x minus a is the difference between the x values. So that expression that they had you simplify earlier on is just an algebraic expression for the slope between 2 points. And now here's the cool thing that happens in calculus. If you've seen this before, or if you haven't, that parabola does not have constant slope. The slope is changing, it's curving around. And so to get the slope at a point, you kind of imagine the point A approaching the point X. And in calculus, they'll talk about that as A approaches X, and they'll use the word limit. So as A gets closer and closer to X, then that slope becomes more and more exact. And there's some calculus tricks here to formally do this, but if you let A equal X, you get, that simplifies to 2x plus 2. And that's going to be the formula for the derivative of X. And the derivative is a fancy little function. And in calculus, a lot of the point of the first semester of calculus is figuring out rules for how to find that function without doing all the algebra. You should be able to, you get to a point where for a lot of functions, you can just look at it and tell me the formula for the derivative, which is, when you think about it, kind of amazing. But that's what happens in calculus. And so what happens is we find a formula for this derivative function, which they call f prime. And it's 2x plus 2. So what does that have to do with anything? I think I have it drawn in the next point here. If you look at this parabola, the red parabola, you tell me a value that you're curious about. For instance, down here at the bottom, at x equals -1, at the bottom of that parabola, this formula for 2 times x plus 2, if I plug in x equals -1, I get 0. And the slope there is 0. It's flat at the bottom. If I then plug in at x equals 0, this point, it tells me that the slope is 1, which it is. If I plug in x equals 1, I plug in 1 and I get out a slope of 4, which is the slope. At 2, that little formula tells me 2 times 2 plus 2 is 6. So it tells me it's steeper there. Over here on the left side, when I plug in x equals -3, that little formula, 2 times -3 plus 2, tells me the slope there is -4. That's a magic little formula that the slope f prime of x is 2 times x plus 2. That gives me the slope at any value along that parabola, right? And maybe you can y prime equals 2x plus 2. And so there are formulas and rules that you see in a calculus course that let you go from the original function, in most cases, and find the function that tells you the slopes, which is called the derivative. So that's a brief introduction to calculus, just a foreshadowing, but that's why that expression g of x minus g of a over x minus a shows up, why you might be curious about that. So work on the other homework problems in this set, and we can talk about those in class tomorrow. Hope that goes well. Have a good night.